the first section of chapter 5, dynamics, and this section is about motion in a straight line with a variable force. Now, a variable force can be a variable force which is a function of time, so the force changes as the time changes, it's some sort of function of time, or a force can be a function of displacement, so as the displacement changes, the force changes maybe proportionally to it. There's going to be some sort of function that gives us force, and it's going to be in terms of x here, displacement, and in terms of t here. So let's start by looking at how we can derive some sort of formula that we can use when we've got force as a function of time. So we start with F equals ma. Now a is what we get when we differentiate the velocity with respect to time, dv dt. So in the second line of work in here, we replace a with dv dt. Then we separate out the variable, so we just multiply both sides by dt, so we get f dt, and then we're just left with m dv on this side. Then we integrate both sides, so you have the integration of the force with respect to time, which is what we want because f is going to be a function of time. And then we integrate the m with respect to v. Now m is the mass, and so it's just a constant. So when we integrate a constant, we will get mv. So our final expression is going to be the integral of the force written as a function of time, integrated with respect to t, equals mv plus, and then we're going to have a constant of integration. So now let's look at deriving an expression for force as a function of displacement. So again, we start with F equals ma. And when we went through section 4.2 from the Further Mechanics 2 book, we derived this expression that acceleration is equal to v dv dx, which is equal to d dx half v squared. Now we're going to replace a with v dv dx. So we've got that here. So we've now got F equals m v dv dx. There's a substitution there. Then we're going to separate out the variables, multiply both sides by dx. So we get f dx and then mv dv. We're going to integrate both sides. Now this is what we want here, since function is going to be force is going to be a function of displacement. So we can integrate it with respect to x, which is what we want. This is going to be a function of x equals mv dv. Now m is just a constant, so when we integrate this, it will be half mv squared, then our constant of integration. So our full expression, when we've got force as a function of displacement, is the integration of f with respect to x equals half mv squared plus c, our constant of integration. Example 1. A particle p of mass 0.5 kg is moving along the x-axis. At time t seconds, the force acting on p has magnitude 5t squared plus e to the power 0.2t newtons and acts in the direction OP. When t equals 0, p is at rest at O. Calculate, first of all in part A, the speed of p when t equals 2. So I can see here that the force is a function of time because it's got t in it. So that means I'm going to be using this expression, the integral of f integrated with respect to t is equal to mv plus c. So this is what I'm going to use to answer part A. So first thing I need to write down is the integral of that function of the force is 5t squared plus e to the power 0.2t is equal to m, so the mass is 0.5 v plus c. I'll start by integrating the left hand side, and that will give me 5 over 3t cubed. Then integrating the e to the power 0.2t, so we use the reverse chain rule. So the e is going to stay as it is, the power is going to stay as, but then we need to divide it by 0.2. So you basically got 1 divided by 0.2, which is 5. So that's the 1 divided by 0.2 is equal to 0.5v plus c. We want to find c, so we look for some information in the question. When t is at 0, p is at rest. So when t is 0, v is 0, and we can use that to find what c is. So we've got 5/3 times by 0 cubed plus 5e to the power 0.2 times 0 is equal to 0.5, and v is 0 times 0 plus c. Right, so let's work this out. So obviously this part is 0. Now be careful here, because e to the power 0 is 1, so we have 5, and basically just end up with 5 equals c, c equals 5. So now we can write our full expression, and that just means replacing c with 5, but I'm going to rearrange it to make v the subject, because I think that'd be more useful. So that means timesing both sides by 2, and then taking the constant of integration over the other side, so I'd effectively have minus 5 there, and so times all of these terms here by 2, so I'll have 10 over 3 t cubed plus 10 e to the 0.2 t, then my minus 5, because I've moved my constant of integration over here, times by 2 will be minus 10, and that will be my expression to find v. So now all I need to do is to substitute t equals 2 into this to find t. So let's do that. V is going to be equal to 10 over 3 times by 2 cubed plus 10 times by e to the power 0.2 times by 2. We'll use our calculator to see what that gives us for v. So the full answer that gives me is 31.58491, and so on. So as usual, 3 significant figures, so we'll do 31.6 meters per second. Right, let's move on to part B, and it says that we want to find the distance OP when t is 3. So if we want to find the distance, we want to find x. Now we know that v is equal to dx dt. So we're going to take our previous answer here, or the previous expression or formula we've got here, and replace v with dx dt. So we'll have dx dt, which is the velocity, is equal to 10 over 3t cubed plus 10 e to 0.2t minus 10, and this is going to be separating out the variables, so we'll put the integration as well. So we'll basically have an integration of dx, we'll times both sides by dt, so that's going to be an integration of 10 over 3t cubed plus 10 e to 0.2t minus 10, all integrated with respect to t. The left hand side is pretty much like integrating 1, so that just becomes x. Then we'll move to the other side. So what we'll have here is that will be 10 t to the power 4, so we got 10 over 3 divided by 4, so that becomes 10 over 12 t to the power 4. For this term here, we're going to have to do 10 divided by 0.2, and that is 50. So we'll have plus 50 e to the 0.2 t, then the minus 10 will just become minus 10t, plus our constant of integration. So I'm just going to use a different letter to avoid any confusion. So I'll just go to the next letter in the alphabet, D. So now we scan the question to see is there information about x and t, so I can find D, and it's here. When t is 0, p is at rest at O, so it's at the origin. When t is 0, x is 0, so that's what we'll substitute in. T is 0, x is 0, so we'll have 0 is equal to 10 over 12 times by 0 to the power 4 plus 5 e to the power 0.2 times 0 minus 10 times 0 plus d. So I just realised that should be 50, not 5. I'm not sure why I wrote 5 down, I actually wrote 50 here. so plus 50. So from this we can work out what d is. So this part's gone, that's 0. This part has gone as 0. So we've got 0 equals 50 plus d, which means that d is equal to minus 50. So our full expression for the displacement distance x is going to be x equals 10 over 12. Let's simplify that to 5 over 6 t to the power 4 plus 50 e to the 0.2 t minus 10t minus 50. And the last bit, we just need to substitute in t equals 3 to find x. So we'll do that now. So x is equal to 5 over 6 times by 3 to the power 4 plus 50 e to the power, well, this is going to be 0.2 times by 3, so let's just write 0.6, 0.2 times by 3, minus 10 times by t, so that's going to be 30, isn't it? So just put minus 30 minus 50. So putting that all on a calculator, I get something like 78.60594. Again, 3 significant figures. So x will be 78.6 meters. So let's just highlight those answers. Part A, v was 31.6 meters per second. Part B, x was 78.6 meters. Example 2. A pebble of mass 0.2 kg is moving on a smooth horizontal sheet of ice. At time t seconds, where t is greater than or equal to 0, a horizontal force of magnitude 2t squared newtons and a constant direction acts on the pedal. When t equals 0, the pebble is moving in the same direction as the force and has speed 6 meters per second. When t, small t, equals big T, the pebble has speed 36 meters per second. Calculate the value of t. So I've highlighted some bits of information, but again on this question, the force is a function of time. So I will use the integral of the force integrated with respect to time is equal to mv plus my constant of integration. So let's start on this question. So here we'll have the integral of 2t squared dt is equal to the mass, which is 0.2 v plus c. We'll do our integration. So 2t squared integrated is going to become 2/3 t cubed is equal to 0.2 v plus c. Now we can use the fact that it says when t is 0, pebble is moving in the same direction as the force and has speed 6 meters per second. So we'll use t equals 0, v equals 6 to find c. So we will have 2/3 times by 0 cubed is equal to 0.2 times 6 plus c. So that will give us 0 is equal to 1.2 plus c, which means that c is equal to negative 1.2. So our full expression is going to be 2/3 t cubed is equal to 0.2 v minus 1.2. So all we need to do now is to substitute in v is 36 to find t. So v is going to be 36. So we have 2/3 t cubed is equal to 0.2 times by 36 minus 1.2. That will give us 2/3 t cubed is equal to 6. So t cubed is going to be equal to 6 divided by 2/3, or 6 times by 3/2. So that's 9. T cubed equals 9. So t is going to equal the cube root of 9. So if we do that on our calculators, cubed root 9, I get 2.080083 and so on. Answer to 3 significant figures, t is equal to 2.08 seconds. Okay, so that will be our answer for this one. Example 3. A particle P of mass 1.5 kg is moving in a straight line. The force acting on P has magnitude 8 minus 2 cos x newtons, where x meters is the distance OP and acts in a direction OP. When P passes through the origin, its speed is 4 meters per second. Calculate the speed of P when x equals 2. So here in this question, I can see that the force is a function of displacement, distance, x. So I will be using the expression, the integral of the force integrated with respect to x is equal to half m v squared plus c. So let's start. We will have the integral of x minus 2 cos x dx is equal to half m is 1.5 v squared plus c. So now we'll do the integration. So I'll have 8x and then cos integrated becomes sine, so it would be minus 2 sine x is equal to a half times 1.5. We'll do that. That's 0.75 v squared plus c. You want to work out plus c. Scan the question. Is there anything? Here we go. When P passes through the origin, its speed is 4. So when x is 0, v is 4. So we'll substitute those in. So I'll have 8 times by 0 minus 2 times by sine 0, which is 0. Be careful, because if that was cos 0, that would be 1. Easy to just write down it's 0. Is equal to 0.5 or 0.75 times by v squared, 4 squared, 16, plus c. So we'll work that out to see what c is. So the left hand side just becomes 0, 8 times 0 minus 2 times 0, so that's 0. Then the right hand side, 0.75 times by 16 is 12, so you get 12 plus c. So that means that c is equal to negative 12. Then we'll have our full expression, which is 8x minus 2 sine x is equal to 0.75 v squared minus 12. Now, since we want to find the speed of P, v, when x is 2, the next bit I don't really need to do, but I'm going to rearrange it to make v squared the subject. I don't need to, I can just plug the numbers in and then work out v squared from there. But yeah, I'll just rearrange it, make v squared the subject. So that means dividing both sides by 0.75. So when we do that, we'll have 32 over 3 x, 8 divided by 0.75. Then minus 2, negative 2 divided by 0.75 will be minus 8 over 3 sine x. The negative 12 is going to move over to the other side, so this becomes plus 12 on this side. Divided by 0.75, it's going to become plus 16. And all we need to do now is to substitute in x is equal to 2 to find v squared and then v. So v squared is going to be 32 over 3 times by 2 minus 8 over 3 sine 2 and remember we'll be in radians, plus 16. Working out on our calculator, we get v squared is equal to 34.9085 and so on. So we'll square root that to find v, and that will give us 5.90834 and so on. We'll give our answer to 3 significant figures. The speed of p, v, is going to be equal to 5.91 meters per second. So that's 3 significant figures. Example 4. A stone S of mass 0.5 kg is moving in a straight line on a smooth horizontal floor. When S is a distance of x meters from a point on the line A, a force of magnitude 5 plus 7 cos x newtons acts on S, the stone, in a direction AS. Given that A passes through A with speed 2 meters per second, what we want to do in part A, first of all, is to calculate the speed of S as it passes through point B where x equals 3. So looking at this question, I can see that the force is a function of displacement, so that means that I'll be using the integral of force integrated with respect to x is equal to half mv squared plus c. Substituting that in, we're going to be integrating 5 plus 7 cos x dx is equal to half times by the mass, which is 0.5 v squared plus c. We will integrate the left hand side. That will give us 5x plus 7 sine x, because cos integrated is sine, is equal to half of 0.5, which is a quarter, v squared plus c. We want to find what c is. Now if we look at the question, it says that we're measuring the distance x from this fixed point A. So A is like our origin, and we're told that when it's at this origin point A, the speed is 2. So when x is 0, when there's no displacement from the point we're measuring from, v is equal to 2. So we'll substitute those in. So that will give us 5 times by 0 plus 7 sine 0 is equal to a quarter times by 2 squared plus c. If we work that out, that will give us basically 0 on the left hand side. Now be careful, if this was cos 0, it'd be 1. If it was e to the 0, it would be 1 as well. So don't always assume you've got 0 that's going to be 0, but in this case it's going to be. So we've got 0 equal a quarter of 2 squared, a quarter of 4, which is 1, plus c, which means that c is equal to -1. So our full expression is going to be 5x plus 7 sine x equals a quarter v squared minus 1. Now since we're trying to find the speed of s, we're trying to find v, it'll probably make sense at this point to make v or v squared the subject. So we'll start by multiplying both sides by 4. So we'll have 20x plus 28 sine x, and then we'll move the 1 across as well, times that by 4, so it becomes plus 4 is equal to v squared. So now I can substitute my values of, or my value of x equals 3, and use that to work out what v is. So x is going to equal 3, so v squared will equal 20 times by 3 plus 28 times sine 3 plus 4, Let's see what that gives us for v squared. So that is 67.9513 and so on. You know, we give the answer to 3 significant figures, so we're going to square root that. And the value we get to 3 significant figures is 8.24. It's like 8.24326 and so on. So 8.24 meters per second. So that's the speed of the stone as it passes through the point B. Now on to part B. On part B, it says the work done, or we need to calculate the work done by the force in moving from A to B. Now, work done is equal to the change in overall energy, and in this case there's no potential energy because it's horizontal, it's just moving across. There is no elastic potential energy because it doesn't involve any springs or strings, anything like that, anything elastic. The only change is going to be the change in kinetic energy. So we're going to work out the kinetic energy when it's at A, and then we're going to work out the kinetic energy when it's at B. Now when it's at A, it's moving with a speed of 2 meters per second. So the kinetic energy at A is half m, which is 0.5, v squared, which is going to be 2 squared. And that's 1. So when it's at A, it's got a kinetic energy of 1 joule. We're now going to work out the kinetic energy at B. Now the kinetic energy at B, now when it's at B, we've got x is equal to 3. We worked that out in the previous part. So we'll use this speed, it's half mv squared. So half m 0.5 v squared. And that's going to be this number here before we square rooted it. So we'll probably just go back on our calculator to get that number back. 67.9513 like this. And when we calculate that, let's see what we get. And that's 16.987 and so on. So I can see the work done is causing the kinetic energy to increase from 1 to 16.987 joules. So the work done is going to be equal to the change in kinetic energy. So that's that 16.987 number, 87 minus the 1. So I can, without a calculator, I can see that's going to be 15.987, 84, so on. I want to give my answer to 3 significant figures, and that's going to be, I'll give 16.0, won't it? 16.0, and work done is measured in joules, so we'll just put down joules at the end of that. Again, 3 significant figures. Example 5. A particle P of mass 0.5 kg moves in a straight horizontal line. When the speed of P is v meters per second, the resultant force acting on P is a resistance of magnitude 3v newtons. Find the distance moved by P as it slows down from 12 meters per second to 6 meters per second. Now you'll notice on this question there's nothing about force being a function of time or a function of displacement distance. So we start with F equals ma. So we'll start with this first. Now we know that A can be replaced with dv dt, or we can replace A with v dv dx. And if we look at this question, we're trying to find a distance moved, that's like x, and we're given velocities, v. So it makes sense to use this expression to replace A with this. Okay, we get the velocity and then we get time, but there's no time in this question. There's distance there's velocity, so we'll replace A with v dv dx. So now we can write F is equal to mv dv dx. So now we'll start to fill in the information from the question. Now it says that F is a force, or the resultant force is a resistance of magnitude 3v. If it's a resistance, then it's opposing the direction of the particle P, so it'll be minus 3v is the resultant force, is equal to m, which is 0.5 v dv dx. So we're now going to separate out the variables. So we're just going to leave actually 1 on the left hand side, so we'll just have the integral dx is equal to, and then it'll be 0.5v divided by negative 3v dv, and that we'll integrate that as well with respect to v. So if we integrate the left hand side, that just becomes x, because it's just like a 1 there, invisible 1 there. Then on the other side, if we simplify it, then the v's will cancel out, and this fraction here will become minus a 6, 0.5 divided by minus 3 minus a 6. So then if we integrate that side, we'll have x is equal to a 6v and then plus c, our constant of integration. Now since we want to find the distance, it moves from basically the 12 meters per second velocity or speed to the 6 meters per second. We'll take this as the initial position because we're measuring the distance from that point. So that will mean that we're going to substitute in x is 0 and v equal to 12. So that will give us 0 is equal to 1/6 times by v, 12, plus c. 1/6 times by 12 is 2, so we've got 0 equals 2 plus c, which means that c needs to equal negative 2, and then our final expression is going to be minus 3v is equal to 0. Sorry, I'm looking at the wrong expression here. I should be looking at this one here. So x is equal to 1/6v minus 2. Okay, so we know that the 12 meters per second point is where x equals 0. So let's just write that down. When v is equal to 12, that gives us x equal to 0. So we just need to work out what's the value of x, not v, the value of x when v is equal to 6. So when v equals 6, what we'll have is x is equal to 1/6 times by 6 minus 2. So that's basically 1 minus 2, so that's negative 1. So that means the difference between the displacements here, 0 and minus 1, it sort of moved backwards by 1. Well, we take the modulus of that, so the distance moved is just going to be a distance rather than displacement. So the displacement would be minus 1 meters, but we want the distance, so the distance is just the modulus of that. The distance is just going to be 1 meter. Example 6. A particle P of mass m is moving along OX in a direction of x increasing. At time t, the only force acting on P is a resistance, so it's going to be a negative force of magnitude mk bracket c squared plus v squared, where v is the speed of P and c and k are positive constants. when t equals 0 and P is at the origin and V is equal to big U, capital letter U. The particle P comes to rest at the point A. In part A we need to find a distance OA. So we start with F equals MA. We write down the force, which is negative MK since it's a resistive force. C squared plus V squared is equal to MA. We can cancel out the M's on both sides. And then we need to think, right, what am I going to replace A with? Am I going to replace it with dV dt? Or am I going to replace A with V dV dx? dV dx. Now, the hint's always going to be, what do you need to find? Distance or time? I need to find distance, so I replace it with this form here. So that will give me negative k c squared plus v squared, c squared plus v squared is equal to, and replace A with v dv dx. We'll now separate out the variables, and I'm going to leave the negative k on the left hand side and then bring the dx over. So when that's integrated, that'll just become negative kx is equal to, and this will become v over c squared plus v squared dv, and again we integrate that side as well. Okay, so what I'm going to do first of all is look at the right hand side. Actually, let's move that. Well, I can move the negative and the k over, they're both constants, aren't I? So I could just put negative k and then the integration there of dx, or like the integration of 1. Yeah, on the right hand side I need to think, well, what method can I use to integrate this? The top is like the bottom differentiated, so this is like the f dash of x, but this would have 2v if that were the case. So I will make it 2v, so it is exactly the bottom differentiated, and then add my adjustment over here, half, to keep it all balanced, and then that way I know, right, it's just log of the bottom. So I will get negative kx on the left hand side, on the right side it'll be half natural log of the bottom, so that's c squared plus v squared, and then plus our constant of integration. So now we're going to use this bit of information that when p is at the origin, v is equal to u, and we'll use that to find our constant of integration. So x is 0, v is equal to big U, we'll substitute those in. So we'll have negative k times by 0 is equal to a half natural log of c squared plus u squared plus c. Now thinking about it, seeing as c is already a constant here, to avoid confusion, and that's like little c, I'm going to change this constant here to d, and that will avoid any confusion. It's a different constant to the one that's in the bracket here. So since this side is equal to 0, that will give me that my constant of integration, which I've now called d, is equal to negative half log c squared plus u squared. Then my full expression here, now replacing d with what I've worked out, is negative kx is equal to a half natural log c squared plus v squared minus a half natural log c squared plus big U squared. So now I can use this expression to find the distance OA. I know that x equals 0 here, so I'd basically want to find the value of x at the point A. If it comes to rest, that means that v is going to be equal to 0. So we plug that in, and then I'm going to tidy this all up in a moment. Negative kx is equal to half natural log, and it's just going to be c squared. The v squared is nothing, minus a half natural log c squared plus u squared. I basically want to make x the subject, so I'm going to divide both sides by negative k. Now if I do that, I can then take out a factor of a half, and also the k that I'm dividing by. Let me just write that a bit bigger. So what I'm doing is I'm taking out half as a factor. I'm dividing both sides by negative k. Now when I divide by negative k, what happens is these are going to switch signs. This is going to be the plus term, and this is going to be the minus term. Okay, so it's actually going to look like this now. So natural log c squared plus u squared minus natural log c squared. And then what we can do is we can put those logs together. Should put x is equal to here. So x is equal to 1 over 2k, and then the natural log of, we will have c squared plus u squared divided by c squared, like this. So that represents our distance OA. Right, let's have a look at part B. Let's make a little bit of space at the top here. And then part B says the time it takes from P to travel from O to A. So again, we start with F equals MA. And in the last bit, we wanted to find the distance. So we use V dV dx. This time we want to find the time. So we use and replace A with dV dt, so that we can get an expression that has t in it. So our force is the same, that resistive force of negative mk c squared plus v squared. Is it equal to m times by A, which is going to be dV dt. We can cancel out our m's like this. Then separate out the variables, and we'll have negative k and an integral dt, so it's like integrating 1, is equal to, now we'll have 1 over c squared plus v squared dv, and again integration of that side as well. So the left hand side is going to become minus kt, and then the right hand side here, you may not necessarily recognize this, but it actually follows this pattern here. We've got a constant squared plus x squared, that's v squared, but it's with respect to v. It's one that's in the formula book from core 2, and we can use the result that it's 1 over a arctan x over a. In our example, a is c, so just using that result, the right hand side is going to become 1 over c arctan, and it's not x, it's going to be v over c, and then plus our constant of integration. Oh, and again, let's use a different letter. Let's use the letter e, so it's not confused with this constant here. So we want to find this constant e, so we need to substitute in t and v, but we know that when t is 0, v is equal to u. So t equal to 0, v equal to big U. So we'll substitute those in. So we'll have minus k times by 0 is equal to 1 over c arctan big U over c plus e, which means that E is equal to negative 1 over C arctan big U over C. So our full expression is going to be minus KT is equal to 1 over C arctan V over C minus 1 over C arctan U over C. So now we're ready to find the time it takes to travel from O to A. Well, we know that when the particle's at O, T is 0. So we just want to find out what's the value of T when it's at A. And we know when it's at point A that it comes to rest. So V is equal to 0. So we will substitute in V equal to 0. Right, so the 0 will go here. We'll end up with arctan 0, which is 0. So all of this part here just becomes 0. So we're just going to be left with this. Now I'm also going to divide both sides by negative k to get the final expression for t. So if I divide both sides by negative k, there's going to be a k at the bottom here. That negative will go. So it'll be 1 over kc arctan big U over C. And we'll just highlight that. Example 7. A car of mass 800 kg travels along a straight horizontal road. The engine of the car produces a constant driving force of magnitude 2000 newtons. At time t seconds, the speed of the car is v meters per second. As the car moves, the total resistance to the motion of the car is of magnitude 400 plus 4v squared newtons. The car starts from rest. I think this question is deserving of a force diagram so we can see exactly what's going on. So this is going to represent my car here. This is going to be my direction of motion. We're told it's moving with a speed of v. The driving force is 2000 newtons, so that's going to be 2000 this way, 2000 newtons. And the resistance to motion is going to be 400 plus 4v squared newtons. The mass of the car is 800 kg, so its weight is 800 g, and there'll be a normal reaction here on our diagram. And in part A, what we need to do is to find V in terms of T. Now, this bit, the finding V in terms of T, tells me that once I've done F equals MA, I want to replace A with dV dt. That will give me the V and the T that I need for the expression for this answer. So we start with F is equal to MA. We'll replace the A with dV dt, like this, and then we can put in our resultant force and the mass and so on. Right, so let's do that. So the resultant force is, this is the direction of motion to the right, so it's going to be 2000 minus 400, put it in brackets, plus 4v squared. That's my resultant force, F, and that's going to equal 800 dV dt. So let's see if we can simplify this a bit. So 2000 minus 400, that's going to be 1600 minus 4v squared is equal to 800 dV dt. Let's divide both sides by 4, make the numbers a little bit smaller. So we'll have 400 minus v squared is equal to 200 dV dt. then what we'll do is times both sides by dt. So we'll separate the variables and just have the dt there, and then the other side we're going to divide by 400 minus v squared, and that will be dv, and mustn't forget my integration symbol here as well, separating out the variables. So if we integrate the left hand side, that just becomes t. Now on the right hand side we could use partial fractions, but there's another result, just like the previous example, that we can use from the formula book, and that's if we see this pattern, the integral of 1 over a squared minus x squared, we can use this result. It's also equivalent to 1 over a arctangent x over a, but I think in this particular example using the log form may be more useful, because I want to rearrange it to make v the subject, and it's probably going to be easier to do when it's in log form. And then at part B, when we're trying to work out the maximum or minimum of it, an expression, again that's going to be easier to do when it's in log or e to the x form. So the right hand side, I can take the 200 over, so it becomes 1 over here, and then I can just apply this result. So it'll be equal to 200, so that's my constant moved over, and then using this rule here, I will have my a is equal to the square root of 400, which is 20. That's nice. Okay, so a is equal to 20, and obviously where I've got x, I need to make sure that I put v there instead. So my result is going to give me 1 over, so I'm just doing this part here, 2 times a, 2 times 20, which is 40, natural log, and then it's going to be a plus x, 20 plus v, 20 plus v over 20 minus v. That saved us a lot of time. It means we've not had to do partial fractions. Now I mustn't forget my constant of integration, so let's call that c. We're told that the car starts from rest, so that means that when t is 0, v is 0, so we'll have 0 is equal to 200 times by 1 over 40 natural log, and then here we'll have 20 plus 0 over 20 minus 0, so log 20 over 20, or log 1, and log 1 is 0, so effectively what we have is 0 equals 0 plus c, which means that c is equal to 0. So the rest of this question now is just rearranging this expression with c equals 0 to make v the subject. So with the 200 divided by 40, that's 5, so basically this bit becomes 5. I'm going to start by dividing both sides by 5, so I'll have t over 5 is equal to natural log 20 plus v, 20 minus v. Like this, I'll do e to both sides, so I'll hit e to the power t over 5 is equal to 20 plus v over 20 minus v. We'll times both sides by 20 minus v, so I'll have 20 e to the t over 5. Hope you can see that there. T over 5 minus v e to the t over 5 is equal to 20 plus v. What I'll do from here is bring the v terms to both the same side and factorise them. So I'll have v, and let's see, I'm going to move this term over to this side, I think. So that will be 1, and then that will be plus e to the t over 5 is equal to, and then I'm going to move the 20 over to this side and again factorise it because 20 is going to be a factor, and then it will be e to the t over 5 minus 1, and then from there I can write down an expression for v which is going to be 20 bracket e to the t over 5 minus 1 over 1 plus e to the t over 5. So that last bit, basically all the working down here is just algebraic. It's just making that v the subject of that whole expression thing, formula we've got there. So part B now, we need to show that the speed of the car cannot exceed 20 meters per second. Okay, so the expression we've got for the speed is this: 20 e to the t over 5 minus 1 over 1 plus e to the t over 5. Now, because it says speed, it could be that v is negative, but it's not larger than or smaller than negative 20 or bigger than positive 20. So we really want to sort of take out the bit that's changing the 20, and it's not going to be the 20, it's the rest of it here. It's going to be that e to the power t over 5 minus 1 over 1 plus e to the t over 5. And we're interested in, well, what happens with all of this is for any value of t, what are we going to be multiplying 20 by? We really want this bit to be less than 1. That way we're always going to have a velocity less than 20. So whether this is positive or negative, we want the modulus of this to be less than 1. Now, we've done something similar to this before, where we've got this part and this part are the same. Okay, one of those numbers is, or values, the numerator is always going to be slightly smaller than the denominator. They're going to be very close numbers as t gets larger, but you're going to have a number which is slightly smaller than the number at the bottom. So basically, for all values of t, that whole expression there is going to be less than 1. It can never be greater than 1. Whenever you have a fraction where the top is smaller than the bottom, even if they're very close, it's still going to be less than 1. So from that we can say, therefore, v is always going to be less than 20 meters per second. So you should now be able to do exercise 5A on pages 179 to 181, and some questions, some of the examples we did, force wasn't given as a function of time or displacement, but we worked out a resultant force. We used F equals ma. If it's a question that involves velocity and time, replace a with dv dt, or if it's a question that involves velocity and displacement, use or replace a with v dv dx.